Welcome to the deep dive. Ever held a seemingly simple plastic part and wondered what really goes into its cost, especially when it's made overseas, say in China?
It's a great question.
Today, we're diving into exactly that, the economics of plastic injection molding. We've looked at industry reports, some academic analysis,
hmm
and our mission is to pull out the key cost drivers for you, the listener. Sort of
Yeah.
the essential knowledge without getting buried in details.
Yeah, and it's fascinating because that little plastic piece, well, the final price tag is way more than just the plastic itself or, how fast a machine runs.
Okay.
It's this whole mix of upfront money, per item costs, running expenses, and even what happens after the part pops out of the mold.
Right, so let's break down those main categories. First, that big upfront hurdle, the tooling, the actual
The
mold.
mold itself, yeah.
Yeah.
Designing it, fabricating it, often using pretty advanced stuff like CNC machining or EDM.
Then you have the costs that stack up with every single part made.
Exactly, the variable costs. That's your raw plastic resin, the time the machine spends making the part, the cycle time, and any direct labor involved.
Okay, tooling, variable costs. What else?
Then there are the indirect costs. Think ongoing operational stuff,
Right.
overhead, like the electricity bill for the factory, rent, and importantly, mold amortization.
Amortization based, the mold paying for itself over time.
You got it. Spreading that initial big cost over all the parts it produces. And finally, don't forget secondary costs.
Like finishing touches.
Yeah, cleaning up the part, maybe assembly, definitely packaging.
Yeah.
And critically for the China angle,
Mm.
logistics, shipping, and potentially tariffs, like the U.S. Section 301 tariffs on Chinese molds specifically.
Wow, okay. Lots of buckets. And underlying all this is a basic economic idea, right? Volume is king.
Absolutely fundamental. The more parts you churn out, the thinner you spread that fixed tooling cost. Makes each individual part much cheaper.
Makes sense. So let's dig into those primary drivers now, starting with the actual plastic, the material itself.
Right. Material selection isn't just about finding the cheapest resin per pound or kilo. You've got your basic commodity plastics like polypropylene or polyethylene.
The common stuff.
Yeah, cheaper. Then you have engineering-grade plastics, polycarbonate, nylon, peak mid-pricier, better properties.
Yeah.
But then you add things into the plastic.
Additives.
Exactly. Colorants, UV stabilizers, fillers like glass fiber.
Yeah.
They all tweak the properties, but also the cost. And interestingly, sometimes making a part white or clear can actually increase molding challenges and cost a bit more.
Huh. And the material affects how it's processed too.
Definitely. Higher melting points mean more energy consumption. Abrasive fillers might require tougher, more expensive tool steel for the molds that doesn't wear out quickly.
And you're always using a bit more material than just the part volume because of the runner system.
Good point. Especially with cold runner systems where that plastic in the channels gets solidified and is often waste or needs regrinding. And a crucial point when sourcing from China. Quality assurance. Verifying the resin grade. You might even need independent testing to make sure you're not getting a substandard material. It happens.
Okay, so material is complex. What about the actual design of the part? How much does that influence the price?
Oh, hugely. Part design complexity ripples right through to the mold costs and potential production issues.
Like if it has lots of weird shapes?
Yeah, intricate geometry, ribs for strength, walls that aren't uniform thickness, sharp internal corners, those all make the mold harder and thus more expensive to machine. They can also lead to defects like sink marks or warp. Using radii, smooth corners is really key.
And tolerances. How precise does it need to be?
That's another big one. Standard tolerances are maybe around, say, plus or minus 5/1000ths of an inch. If you need tighter control than that.
More cost.
Definitely more mold cost, potentially slower cycle times for quality checks. Wall thickness is also critical. You want it as uniform as possible.
Well, uniform.
Because the thickest section dictates how long the part needs to cool in the mold. And cooling is often like 80 or 90% of the entire cycle time. Thinner, uniform walls mean faster cooling, faster cycles, lower cost.
Got it. What about things like undercuts, those features that prevent the part from just popping straight out?
Undercuts require complex mold action sliders, lifters mechanisms that move within the mold. Big cost adder for the tool.
And the surface finish, glossy versus matte.
Yep, that matters a lot for the mold cost. Basic finish is cheapest. Textured finishes need etching. High gloss finishes, like for lenses or premium electronics.
Requires a lot of polishing.
A ton of highly skilled, expensive hand polishing on the mold cavity. We're talking different SPI grades, which are industry standards for finish. Even the parting line where the mold halves meet, keeping that simple and straight, minimizes issues. Oh, and draft angles.
Angles so the part releases easily.
Essential. Forgetting draft means parts get stuck, potentially damaging the part or the mold. Adds cost one way or another.
Okay, so simpler, well-thought-out designs save money. What about just the sheer size and weight of the part?
Pretty direct impact, that one.
Yeah.
Bigger part, more plastic, higher material cost. Simple.
And bigger molds, too, I assume?
Bigger, heavier, more complex molds, which are significantly more expensive. Plus, you need bigger injection molding machines, which have higher clamping force measured in tonnage.
And those machines cost more to buy and run.
Correct. And larger parts generally take longer to cool, stretching out that cycle time again.
Right, back to cycle time. Now, production volume, we touched on this with amortization, but how does the planned volume affect decisions up front?
It fundamentally dictates the mold strategy. For, say, prototypes or very low volumes, you might use an aluminum mold. Cheaper, faster to make, but doesn't last long.
Okay.
For medium volumes, maybe a softer P20 steel. For high volume, long-running production, you need hardened tool steels like H13. Much more expensive, but lasts for potentially millions of shots. There are SPI classifications for molds based on expected lifespan.
And verifying you get the right steel grade is important.
Crucial, especially overseas. For really high volumes, you might invest in multi-cavity molds.
Making multiple parts in one cycle.
Exactly. The mold costs way more upfront, but your per-part cost plummets because you're getting, say, 4, 8, or 16 parts every cycle instead of one. Family molds making different parts in the same mold are generally discouraged, though harder to control quality.
And China's strength is often in these high volumes.
Absolutely, they have massive capacity for high-volume manufacturing. Just be aware, suppliers, especially in China, often have minimum order quantities, or MOQs.
Can't just order 10 pieces usually.
Right.
Okay, cycle time again. You said it's maybe 60% of the part cost.
Around that, yeah, it's a huge driver. It's basically the machine time plus the associated labor for that cycle. And like we said, cooling time is the dominant factor.
80% or more.
Often, yeah. It's influenced heavily by that max wall thickness. There's actually a squared relationship, so doubling thickness can quadruple cooling time. Also depends on the plastic's thermal properties and how well the mold's cooling channels are designed.
So mold design impacts cycle time too.
Big time. Other parts of the cycle, injection time, mold opening and closing, part ejection, they add up. But cooling is usually the longest phase. Hot runner systems can sometimes speed things up by eliminating the runner solidification time, but they add cost and complexity to the mold.
Can you estimate cycle time beforehand?
You can. There are formulas, rules of thumb, but for accuracy, mold flow simulation software is often used during the design phase.
Okay, let's talk more about that mold tooling cost, the big upfront one.
Right, the single largest initial investment, typically. We mentioned amortization spreading that cost. Key factors are the initial price of the mold, its expected lifespan in shots, and the total number of parts you'll produce.
What's a typical mold cost? Is there a range?
Oh, it varies wildly. A simple, small, single-cavity mold might be a few $1,000s. A complex, large multi-cavity mold made from hardened steel could easily run into the hundreds of thousands.
Wow. And payment terms are important, especially in China.
Extremely important. Usually it's something like a deposit to start, another payment after sample approval, T1 samples, and the final payment upon shipment.
Wow.
And absolutely critical, define mold ownership clearly in the contract.
So who owns the tool is spelled out.
Yes, you paid for it, you should own it. Prevents the factory from using it for other customers or holding it hostage. Also need clarity on who pays for maintenance and repairs. Risk of premature mold failure is real if it wasn't built to spec.
Makes sense. Now, labor costs, that's often cited as a major reason for going to China.
It is, undeniably. The hourly rates for factory workers, technicians, even engineers are significantly lower in China compared to, say, the US or Western Europe. Maybe $3.70 to under $20 an hour versus $40 plus.
And that affects mold making and part production.
Both. Labor is a big chunk of mold building cost, and direct labor is part of the variable per part cost tied to cycle time.
But it's not just the hourly rate, right?
No, you have to consider nuances. Productivity levels, the degree of automation in a specific factory. Sometimes lower labor costs might mean more manual inspection is needed, which adds back cost. Communication inefficiencies due to language or time zones can also effectively add cost.
Okay. What about after the part comes out of the machine? Finishing and secondary operations.
Right. The part isn't always done when it ejects. It might need digigating, removing the runner, trimming flash, maybe surface treatments like painting, plating, or pad printing, texturing, sometimes assembly with other parts, labeling, specific packaging.
And these all add cost.
Of course, they add labor time and sometimes material costs. Things like printing or plating could add, say, $25 to $1 per part, just as a rough idea. China can be very competitive for these manual secondary ops.
But again, quality control is key.
Absolutely crucial for secondary ops. Need clear standards and checks.
And what about just the cost of running the injection molding machine itself?
Yeah, the machine operating cost, often calculated as a machine hour rate. This bundles in energy consumption, which could be significant maintenance, repairs, maybe a portion of the factory overhead, and the depreciation of the machine itself.
And those rates differ.
Significantly. Chinese machine hour rates might range from maybe $8.50 to $80 an hour, while U.S. rates could be $75 to $150 or even higher. But it really depends on the size and sophistication of the machine.
Okay, so bringing it all together, focusing specifically on manufacturing in China, what are the big picture pros and cons?
The main advantages, the China advantage, are generally those lower labor costs we talked about, huge economies of scale, a very developed infrastructure and supply chain for manufacturing, often faster speed and lead times, maybe even 50% faster for tooling sometimes, and overall competitive pricing, potentially 20–60% lower total cost.
And the cost breakdown for a mold made in China.
Typically, the steel and components might be 20–35% of the cost. Machining is a big chunk, 25–40%. Design maybe 5–15%. Assembly and fitting, 15–20%. Testing is usually small, under 5%. And then there's tax and the supplier's profit margin, maybe 15–30%. Sometimes people use a rough price factor, material cost times 2.5 to 5, but that's very crude.
But it's not all smooth sailing. What are the hidden costs or risks?
Definitely risks. Logistics and shipping are big ones. Sea freight is cheaper but slow. Air freight is fast but very expensive. You need to understand Incoterms like EXW, FOB, CIF, DDP, which define who pays for what and where responsibility transfers.
And tariffs.
Yep, tariffs and duties. That U.S. Section 301 tariff adds a hefty 25% onto Chinese molds imported into the U.S. You need to verify the correct Harmonized Tariff Schedule, HTS codes.
Quality control seems like a recurring theme.
It is paramount. You keep crystal clear specifications, maybe factory audits beforehand, then robust inspection processes, checking incoming materials, in-process checks during production, and definitely pre-shipment inspections. Reviewing those first samples, T1 and T2, is critical. Maybe even coordinate measuring machine, CMM, reports for critical dimensions.
What about just managing the project?
Communication can be a challenge. Language barriers, time zone differences, cultural nuances in business communication. It requires effort and clear processes.
And protecting your design.
Intellectual property, yes. Standard NDAs aren't always effective in China. You need China-specific NNN agreements, non-disclosure, non-use, non-circumvention, drafted by lawyers familiar with Chinese law, and again, clearly define that mold ownership.
Any other risks?
Mold modifications or repairs, if needed later, can be costly and cause significant delays, especially managing that remotely.
Okay, this is a lot to juggle. For someone listening, trying to get a handle on estimating potential costs, what are the key takeaways?
Well, first, know that resin prices change. ABS, PP, PC, nylon, they all have different typical price ranges. Maybe look up indicative USD per kilo prices, but always get current quotes.
Okay.
Remember that for molds made in China, machining and the steel itself are usually the dominant cost factors. Per part costs will swing wildly based on your volume, and the complexity of the part low, mid, high volume examples show huge differences.
And comparing quotes.
Yeah, case studies often show tooling costs in China can be dramatically lower than in the US or Europe, but part price differences might be smaller depending on automation levels and other factors.
But the most crucial point.
The absolute bottom line is this. All these numbers, these percentages, they are estimates, educated guesses at best. To get real accurate costs, you must prepare a detailed request for quotation in RFQ.
What goes into a good RFQ?
You need clear 2D and 3D CAD drawings, precise material specifications, including grade and any additives, defined tolerances, the required surface finish, mentioning SPI grades helps, your expected annual production volume, packaging requirements, and any specific quality control standards or testing needed.
And send that to multiple suppliers.
Absolutely. Get quotes from several qualified suppliers, both potentially domestic and overseas, to make an informed decision. Don't just go with the first number you see.
So wrapping up our deep dive today, it's really clear that figuring out the true cost of an injection molded part, particularly when sourcing from China, well, it's complex. It's not just one number.
Not at all. It's a web of interconnected factors. What really stands out is how those initial design decisions, wall thickness, complexity, material choice, have such a massive downstream effect on everything from tooling cost to cycle time to final part price.
Yeah, the ripple effect is huge.
It really is. And that brings up a final thought, something for you, the listener, to consider. Knowing how tightly linked design complexity and production volume are, particularly with the added layer of international manufacturing. What specific aspect of your next project, maybe a design feature or a material choice, will you approach differently now, having peeled back these layers?
That interplay between design and volume seems critical.
It's perhaps the key relationship we've uncovered today. Understanding it is how you move from potential pitfalls to, hopefully, significant manufacturing advantages.